right, any questions? Okay. All right, so how fast does a 12-foot car need to travel in order to fit inside an 8-foot garage? All right, so the two basic principles we've dealt with so far are time dilation and we have the formula that time is equal to gamma times proper time, where gamma is 1 over the square root of 1 minus beta squared, and beta is equal to V over C. And length contraction. Those are the two math bits that we've dealt with. Proper length is equal to gamma times length. And then we got into the idea of simultaneity. I think it's spelled right. That's a T there. Apparently, I'm doing something I'm not supposed to do. And the idea of simultaneity is two things that happen simultaneously in one reference frame do not happen simultaneously in another frame. The idea of time dilation is that if I'm traveling, as I travel closer to the speed of light, that biologically I will not age as fast, time will not pass as fast as for someone who's not traveling at my speeds. And then for length contraction, if I'm traveling near the speed of light, things will appear shorter. Well, no, let me strike that. As I observe something traveling faster, getting closer to the speed of light, it will not be as long as it is if it's at rest. So, let's approach this from one point of view. I know that the difference between 12 and 8 are, we have gamma is going to pop into it somehow. What's the smallest value that gamma can be? How would you get 0 from 1 divided by something? How do you get 0?
I just asked.
This is a math question, not a physics question. What's the smallest value that this can be, given that beta will never be bigger than 1? Well, actually, yeah. Beta will actually equal 1 for anything with mass. Someone want to take a shot besides Gina? Yeah. Gamma is equal to 1. In other words, time for one person is the same as time as the other, as long as their relative speed is 0. So when beta is 0, we get 1 divided by 1. So gamma is always going to be bigger than or equal to 1. We also calculated some values for gamma, and we never got anything less than 1. So if I've got 8, 12, and a gamma here, I know that gamma is equal to LP over L. I got two numbers there. Which one, how do I stack it up?
12 over 8.
Yeah. Which is 4/3. So I know that 4/3 is equal to 1 over the square root of 1 minus beta squared. And I'm trying to solve for beta. So what do? What's the math? It's okay to speak. What's the first step?
Multiply both sides by the square root of 1 minus beta squared.
Alright, so we got square root of 1 minus beta squared times 4/3 equals 1. Then,
Multiply by 3/4.
okay. So square root of 1 minus beta squared is equal to 3/4.
Square both sides.
So 1 minus beta squared is equal to 9/16.
Subtract 1. Or subtract 16 over 16.
Subtract this.
No, the 1. From the left side.
Say it again.
Subtract the whole, like, 16 over 16 by both sides to get rid of that 1.
Oh. So subtract 16 over 16. So I got negative beta squared. So I'm subtracting 1 from each side, so that's negative 7/16.
Multiply by -1 and then square root it.
Alright, so beta is the square root of 7/16, which is
0.661.
so if I want to know the speed, 0.6, saying beta equals 0.661 is fine. It does not require any units. Or if you wanted to take the next step, you could just say the speed is 0.661 times the speed of light. Now, whose point of view? The car's point of view or the garage's point of view?
The garages.
Right. Because from the garage's point of view, the car is traveling at 0.661 times the speed of light, and so the car will appear smaller. Well, not appear, the car will be smaller. Then from the car's point of view, the garage is smaller. So from the car's point of view, it will not fit inside there because in essence, the garage is now 3/4 of the size that it was. So how do we resolve this idea of the fact that from the garage's point of view, the car has gotten smaller and can fit inside, but from the car's point of view, the garage is getting smaller and there's no way the car can fit inside? Well, this relates back to simultaneity. So we will revisit a similar problem and try to resolve the issue of the fact that they each claim, the driver of the car and the garage itself will give it sentience, will both claim that the other one has gotten smaller. So let's first go do a little Galilean relativity here. I think I did this this before. Okay, third person is throwing a ball, so the velocity of the ball with respect to the car, we'll just say is 30 miles per hour. The velocity of the car with respect to the ground is 50 miles per hour. So the velocity of the ball with respect to the ground is what? So from the car's point of view, this ball's going 30 miles per hour. From the ground's point of view, the car is going 50 miles per hour. So from the ground's point of view, how fast is the ball going?
80.
Yeah, you just add them up. Now, from a vector point of view, vector addition point of view, whenever I'm doing vector addition, it's always the object that has that velocity and then the point of view. So this is the ball from the ground's point of view will be equal to, well, I know that it's the ball there and the observer is the ground there, and so as long as the observer here and the object here are the same, it's completely legitimate. So as long as those two are the same, this is vector addition. Oh, I wanted to do something else first before I did this. I'm gonna leave that there, we're gonna come back to it. Come on. All right, so there's some particle here that is traveling a certain distance. There are 2 points of view. There's what's called the S frame, and then there's the S prime frame. You can think of this as ground and car. And the particle is traveling a certain distance. Now, the S frame and the S prime frame disagree on what the distance is, length contraction. They disagree how much time is involved. So let's just sort of set up not that. Let's set up what we know. I know that the velocity of the particle with respect to S prime, we will make W. Nope. It's as if the W never existed. So you're in the car, you see how fast it's going. Over there, it would be the 30 miles per hour. The velocity of S prime with respect to S, we're going to make how about that? We're going to make U, and the velocity of the particle with respect to S, we're going to make V. So we got, just so I don't have to keep writing subscripts. So what is the relationship between these? Because I think we left off last time with, if you're in the rocket ship going 0.9 times the speed of light and you throw a ball at 0.8 times the speed of light, how fast is the ball going? And we ended up with a velocity or a speed greater than the speed of light, which general special relativity says not going to happen. Well, I know that this is from the S prime point of view, it would be whatever the distance S prime says it traveled divided by the time. So it's the prime point of view, so X prime over T prime. V is going to be X divided by T. It's how far, from the S frame's point of view, it's how far it traveled divided by how much time. So the question is, what's the relationship between X prime and X and T prime and T? Now this is a little bit different than straight up time dilation or length contraction. Because we're talking about length contraction, we're talking about the length at a moment in time, and now we're talking about an event that takes place over a certain amount of time. So we have to somehow take that into account. So again, I'm going to start out with Galilean relativity, and then I'm going to hand wave in the difference between special relativity and Galilean relativity. So if I've got, let's say, a stoplight here, and I have a car that's traveling that way at some speed v, or, yeah, we'll leave it like that. And there's something that's happening over here. The distance from here to here, where this is happening based upon relative to the stoplight, is some distance x. From the car's point of view, this is some distance x prime. This distance here is vt. So we end up with this relationship that x prime plus vt is equal to x. So I have a relationship between, this is the time from the stoplight's point of view, the distance from the stoplight's point of view, and then the distance from the car's point of view. Now in everyday life, when you're traveling the speeds that we normally travel in, that's all you have to do to it. But if I solve for x prime, again, Galilean relativity, good enough. But with special relativity, there's the hand wave. Gamma has to show up somewhere. It's gamma x minus vt. Similarly, you can solve for time t prime, how much time takes place in the prime frame, and that's a gamma t minus xv over c squared. These two things, and then there's the equivalent, you can solve for x and t, and I'll just throw them up for completeness here. T would be gamma t prime minus x prime v over c squared, and x is equal to gamma, oops, sorry, that's plus, do a plus there, is equal to x prime plus vt prime. These are known as the Lorentz transformations. Lorentz was Heinrich Lorentz was one of the movers and shakers in the physics world back in the late 1800s. He jumped through hoops trying to figure out why the speed of the observer or the reference frame made no difference in Maxwell's equation. He came so close to basically beating Einstein to the game, but he just would not accept that the speed of light was constant. He was trying to figure out why our measurements would make it seem like speed of light is constant, but he would not accept the fact that the speed of light was constant. So he gets the transformations named after him, which are used in special relativity. He had done a lot of the legwork by the time Einstein came along and went ahead and made his assumption. so taking this into account, using the Lorentz transformations, this becomes gamma x minus how fast the prime frame is going relative to the S frame. So minus ut and gamma t minus ux over c squared. Questions to hear? All right, I need some room, I'm gonna erase this part. Of course, it's not gonna erase as we go. Right, all right. So now mathematically, I need to simplify this. This is not a particularly usable form here. So I'm going to multiply top and bottom by 1 over t. If you'll notice immediately, we can cancel out the gamma. So gamma's going to disappear from this. Oh, there's no red. I think that'll pretend to be red. That cancels out. We're going to multiply top and bottom by t. And so I get x over t minus u over t, actually, time cancels out there, minus u, over 1 minus u over t, x over c squared. Oop, rewrite that. Minus x over t, u over c squared. That's preferred. Well, what's x over t?